All right, exam 1 is next Thursday in class. So we'll be probably over everything through chapter 11. Yep, open book in class, 2 hours. So plan for that. If that doesn't work into your schedule, I know Kyle leaves pretty much on time. Might not work. He might have to come an hour early, which is fine. I can do that too. So I'll probably send an email out to everybody saying, this is what we're doing. If you got a problem, communicate. Okay. So it'll be like 9 through 11, 9, 10, 11 chapters. All right. And then I put everything on for the whole term, except for the final. I have the final right now, the last day of the term, because it doesn't really work for this Thursday of finals week for me. So we'll see. We'll see just as we get closer, I could move that around. Exam 2 here, all the chapters we're gonna do. So, yep. Clicking right through it, just like you said, it's going by fast. All right, let's go over the homework. I wanna do 1B. So 1B, A just asked you to compute the longitudinal strain in the bar. I think everyone probably could do that just with PL over AE. But B says if the transverse deformation of the rod is 0.0024, transverse deformation 0.0024, and the rod, we didn't have the maybe I do need to do that. Well, we'll see. Compute the Poisson's ratio for the material. So Poisson's ratio is equal to, it's right there on the same page, transverse strain over transverse axial. So since we have the transverse deformation, if we had the axial strain, then we could solve this for Poisson's ratio. So if we remember what axial strain is, again, it's right there on the previous page. Strain is equal to delta over L. Oh, I guess it's the previous chapter. So in this case, we were given the axial elongation and we're given the original length. So we can find this. Then when we have this, we can plug it in here and go after this and Poisson's ratio. So, all right, because they gave us this transverse, I probably am going to have to go back and do part A to get the, because I don't think it gave us the diameter of the rod. Oh, it did, 2-inch diameter. So we're good. Diameter 2 inches. All right, so it does help to like just write it all down. Focus, there we go. So what they want to know in part B is the transverse deformation of the rod is 0.0024, compute Poisson's ratio for the material. So if we know the transverse deformation and we know the transverse dimension of 2 inches, we should be able to get to this strain. This one we can get to from this. So let's do axial strain first, 0.48 inches over, and we don't want 10 feet, we want 120 inches. So those units do have to be the same. Because then we'll get our inches per inch. .48, enter, 120, divide, 0.004 inches per inch. So that's the axial strain. That's using the axial elongation and the original length. So that's part of it. If we can get now the same thing for the transverse, which we should be able to because we know the diameter is 2 and we know the transverse change is 0.0024. So transverse change 0.0024 inches. The transverse original diameter 2 inches. So we use that full 2 inches. Point 0012. So then Poisson's ratio is that relationship between the two strains with the transverse on top, 0.0012, and the axial on the bottom, 0.004. It says it's 0.3 for Poisson's ratio. Now, they gave us this material, right? What was it? It was 1020. Okay, so let's see if that's in the back of the book, because Poisson's ratio is a material property. And let's see if we have a 1020. We do. 1020. And they say Poisson's ratio is 0.25. So we came up with 0.3, kind of a calculated Poisson's ratio. And then the back of the book, its average Poisson ratio is 0.25. So they're close to each other, not perfect, but this was some kind of a measurement system, right? So it was like trying to reverse engineer this to figure out, is this really 1020 steel? I'd say, I don't know. Based on those numbers, 0.3 is not exactly 0.25, but it's close. All right. Then number 7 was a thermal problem. So it says an aluminum wire is stretched between 2 rigid supports. That's important. Rigid supports means this thing is not allowed to deform. So it's stretched between and attached, and it has 5,000 PSI. Tensile stress, I think it says. Tensile stress on the wire is 5,000 PSI at 68 degrees. Then it says, what is it at 32 degrees? So when we cool something down, it wants to do what? Shrink. So that is going to be additive to this 5,000 PSI. So because this wants to shrink, it's actually going to increase the overall tensile stress, right? When it heats up, it's going to relieve it. So that kind of makes sense. So what you have to do is figure out, oh, with that temperature change, 68 to 32, how much stress gets developed? So the stress equation for thermal was alpha E. So this is thermal stress, alpha E delta T. So I hope they gave us this material. Aluminum wire. Perfect. So we got to look up aluminum wire. We got to look up aluminum for the coefficient of thermal expansion and for the modulus of elasticity. So aluminum for the coefficient, 13.1 times 10 to the minus 6. That's inches per inch per degree Fahrenheit. So that is alpha. And then we need E for aluminum. Modulus elasticity, 10,000 KSI. So 10,000 kips per inch squared. That's E. I put a little TH on stress thermal. Now we need delta T. So we need the change between 68 and 32. $36. Exactly. 36 degrees F. Just making sure my units cross. Degrees Fahrenheit go away. Inches squared, kips per inch squared. That's going to stay. That's going to be my unit, KSI. So if I'm adding it to PSI, I'm going to have to figure that one out. Let's see what we get. So this is the stress due to the temperature drop. And it's going to add to the 5,000. It's going to make things worse. 13.16. So I get 169 KSI. Is that what you got? That seems too big. I'm going to do it again. Yeah, that sounds better. 13.1 EE to the minus 6. Yeah, 4.71. KSI, so that is 4,716 PSI. Right? And then we add that to the 5,000 to get a total of tensile stress 9,716 PSI. Just adding that to that. Yeah, inch per inch is not a unit. Kind of hanging out. Now they did give you, this is interesting. They gave you this, just threw this into the problem, proportional limit. No apparent reason why they did that I can see, other than they want you to check it to the limit. So I guess that's what this is for. So we say, oh, 9,716 PSI. That's a lot of tensile stress, but it's still way under the proportional limit. So it's fine. So I'm guessing that's why they tossed that in. Surely not going to need it for the other one, which is the temperature rise up to 90 degrees. So in that case, we have the same kind of numbers. It's going to be this 13.1 e to the minus 6. I'm not going to write the units this time. It's 10,000 KSI for the E value. But now we have a temperature rise from 68 to 90, which is 22. Is that right? 70? Yeah, 22. But this time, this is a rise, and this stress will relieve the 5,000. So we take it away from the 5,000. Yeah. Yep. 68. So the 5,000 was applied at 68 degrees. So that's like your baseline zero. Yeah, I don't do negative and positive. I just think about getting hotter, which means it's going to expand things, which means if it's already got a tensile load on it, it's just going to relieve that stress. So because each problem is a little different. Like if you had something that had a load like pressing on it that was in compression, then you'd have to somehow flip everything. So there is no sign that really makes good sense for me. The only thing, and I say this is getting hotter. This is colder. So you just make some note to know what you got to do to the object, whether you got to relieve the stress or add the stress. So this one looks like it's 2.882 KSI, which is 2008.82 PSI. We would take that away from, because this is expansion and this is tensile stress. So we take that away from the 5,000. Whoa. That won't work. Looks like the stress tensile is 2118 PSI. So because we heated it up, it relieved that 5,000. Here we dropped it down temperature, that increased the tensile stress. That makes sense? Yeah. And the rest of you in online world, I guess, hopefully it makes sense. So remember that chapter 11 is like these very localized stresses. So the first one we did was Poisson's ratio and how that works. And then we jumped into thermal and how that works. And now we jump into combined. It's called multiple materials, but I call it combined because they have to be combined. They have to act together. So it's not, multiple materials is not the first, like they show you a diagram, which is not what it is, this thing. So I don't know why they have this thing in multiple materials, because this is not what we're talking about. And this is not what we're talking about. So what we're talking about is two materials that act together. Like this. So if you have anything else, you have to determine like the stress in each one, like we did on that one problem. This one, they act together. So the key is, do the two act together, and is the elongation of material A and the elongation of material B equal to each other? Like concrete and rebar, those act together, right? If you compress them, they both compress exactly the same. So the whole derivation of the equations is based on this. Elongation of A, elongation of B, exactly the same. So just keep that in mind. If that's not true, then you don't use these equations. If that is true, like this problem here, you know, steel plates somehow attached to the wood to create a column, those two things are going to act together. If that's true, then there's formulas that get developed based on that logic. Okay, there's only a couple of them we're going to use. So I like walking through it. I don't derive a lot of things around here, but this is a good one just to think our way through. We're going to have a new variable and it's n, and it's called the modular ratio. And it is the modulus elasticity of the A material over the modulus elasticity of the B material. How do you know which one's A and which one's B? The largest E value is A. So this is largest, which means the modular ratio usually is, you know, above 1. It's got to be the bigger numbers on top. So, and the only reason we need the modular ratio is it does show up in the load equation. So if you want to know the load, P, on a combined system, a system that has two materials acting together, then they give you this. This is what all this boils down to, the load equation. And in it, you'll see N. There it is. And that's just a modular ratio. So then there's stress in B and some areas. Now, the reason that we put the stress in B in here is because it's the weaker material, right? B is always weaker, A is always stronger. So we set this to the limit. So in this case, the wood would be the weakest. We'd look up the stress of wood, probably parallel to the grain, looks like, and we would put it right in there. Which means it makes sense. The limit of this load is going to be stressing that weaker material out, right? The stronger material is going to be fine. The weaker material is going to get maxed. So that equation works really well. You plug in the limit for the B material, and then you can crunch out the total load on the column, which is often what we want to know. Like, hey, how much will this column take, right? I know it'll take more than what the wood would take alone, but how much more? That's what this tells us. Okay, so that's modular ratio. The other thing you can figure out is from the modular ratio and from this concept of, hey, these elongations are the same, that means the strains are the same. And I know that E equals stress over strain. So then this starts boiling down into this thing right here, which is kind of the relationship between the two stresses. Stress in A, stress in B. So if I wanted to solve for one of them, like, hey, what's the stress in B? It's gonna be this thing, right? Stress A on top, E, A on the bottom, and E, B on top, right? So to get stress in B, we can use this relationship if we know that. So same kind of thing. When you have 4 variables, you got to know 3 things before you can get much done. So those equations are pretty handy. That's this top one. Stress in A is EA over EB. Stress in B, EB over EA. Those just flip. This actually is called the modular ratio. So then they take it down to, hey, the stress in A equals N stress in B. So if we max stress in B, we can use the modular ratio to get the stress in A. Doesn't really help you with the load, but it does help you with, hey, if you wanted to know like how much stress is in the steel or how much stress is in the wood, this will get it to you. This will do it for you. If you want to know load on the column, this will do it for you. All right, so what I want to do is just an example, kind of a real world one where we build a form out of wood. So that's all wood. Pretty common, but sometimes in columns, you'll just leave the wood and you'll load the whole surface. So this would be a concrete reinforced wood column. So I made it 2x8s and I just kind of lapped them. And then that gives me 6x6 in the middle for concrete. So if I wanted to know the load, like how much load will that carry? That would be a multiple material problem because the whole thing's going to act together. So the equation is P equals stress in B, modular ratio, area A plus area B. B material is the weaker material. So I'm going to put in the limit for Doug fir here. Then I need the modular ratio, which is EA, EB. So that's going to be E of concrete and E of wood. Right? Because concrete's clearly stronger than the wood. So it's going to be the A material. Thank you. So let's get the modular ratio first. Look up the elasticity of concrete. modulus elasticity, we'll say it's just average concrete. 3120 KSI. And then we'll look up the modulus of structural timber. That is on page, trying to find it. There we go. Say it's Doug Fir. And modulus elasticity 1700 KSI. Doug Fir is what we use around here. So modular ratio is 3 to 120, 1700 divide 1.835. So that's here in. I need the area of A. So that's the concrete. A material is the stronger material. So this will be 6 times 6, 36 inches squared. And I need the A of the B material. So I need to know how much area is in a 2x8 and multiply times 4. So I'm going to look up a 2x8 because I know that number's in the back. Page 495. Two by 8, area 10.9 inches squared. So area here equals 10.9 inches squared. And I need 4 of them. $43.6. Now I should be able to write the whole equation. P, the load equals, I need the stress in B. B is the Doug Fir. And I need the stress parallel to the grain. So I got to get that one still. This is a compressive stress. Parallel to the grain, that's F sub C. F sub C is 1050 PSI. That's this. Now I need my N. 1.835 times my area A, 36 inches squared, plus 43.6 inches squared, bracket, bracket. I guess only one bracket. 2, 1, yeah. That makes sense? Pretty straightforward. So 36 plus this inside number is 109.66 times 10.050. The load, this thing could hold 115,143 pounds. Because I have pounds per square inch here and that pounds gets left. I have inches squared inside, that crosses with the per inches squared here. So pounds, pounds. So probably written 115.14K. And the way this equation works is it loads the weaker material, the wood, all the way up to its limit. That's why we put that stress of B in here. The concrete's probably not pressed all the way to the limit. More than likely it's not. But the wood is maxed out. So that's a lot of load. Like if it was just concrete alone, let's just calculate that. So if it's just concrete, right? And I want to know the load, I know stress, whoops, that's stress equals P over A. So P equals A times the stress. What was the concrete maximum stress? 3 KSI compression, yeah. 3,000 PSI here. The area is 36 inches squared times 3,000 PSI. $108. Kips. So just the concrete alone will carry 108 kips, right? The combined with the wood and the concrete, we get to 115. So not a lot of advantage having the wood around it, but a little. It did increase it some. Put steel around it, you're going to increase it a lot. All right. Questions? It's pretty straightforward. You just have to remember what material is A and what material is B. Identify it, write it down, so then you get your modular ratio correct. And then you plug in the correct stress here, the weaker stress. Yeah, if you don't know, look up the modular ratios, see which one's stronger. Whichever one's bigger and stronger, then that becomes material A. So you can always look them up. But yeah, the only time it would be weird is if you had like some kind of, you know, steel casing and then you fill it with another steel material or something. The two steels are kind of close. But you just yeah, look it up. And brass and actually aluminum and copper is really common because we use aluminum wires and then we'll coat it with copper. So it'll be a copper coated aluminum wire. Like most of our power generation transportation system is that way. So then between poles, if you're trying to calculate stress or thermal expansion or contraction, you have to do multiple materials. So it's a perfect application. No, gotta look it up. Yeah. Yep, exactly. All right. Before I do this, before I stop sharing, let's look at what the homework is. Chapter 11, 11 and 12. So I think those are both multiple materials. Oh yeah, I wanted to talk about 12. So here's 12. It's a weird image. Oh, I'll share that. Hang on. So number 12 is kind of hard to decipher. What this is a top view. So it's a cross-sectional view looking from the top. So it is a lot like the one we just did or looked at, or the example problem, wherever that is. This example problem, but you're looking at it from the top, kind of like this. So there's an example problem, just like your homework problem. So that was the only thing I wanted to clear up because it's a little odd just looking at it. Steel plate, chunk of wood, steel plate, all acting together. And then, yeah, I think 11's the same kind of problem. So should be just 2 problems practicing multiple materials. All right, good luck.